continuous time case, the constant discrete time signal resulting from setting omega naught equal to 0 as the fundamental frequency is 0, fundamental period also undefined. Okay, then comparison of continuous time signal e power j omega naught t and discrete time signal e power j omega naught e power j omega naught n. Distinct signals for distinct value of omega naught in continuous time signal. Here in discrete time signal, identical signals for values of omega naught separated by multiples of 2 pi. Periodic for any choice of omega naught. Here periodic only if omega naught 2 pi m divided by n. For some integers n is greater than 0 and m. Fundamental frequency here omega naught, fundamental frequency omega naught divided by m. Fundamental period here omega naught equal to 0, omega naught equal to 0, undefined. If omega naught is not equal to 0, then condition is the condition is omega naught equal to not equal to 0. That time 2 pi fundamental period is 2 pi divided by pi naught. 2 pi divided by omega naught. Fundamental period in discrete time signal e power j omega naught n under omega naught equal to 0 in this condition undefined fundamental period. For when omega naught is not equal to 0, that time fundamental period is m of 2 pi divided omega naught. Here assume m and n do not have any factors in common. Here discrete time sinusoid signals. In this figure A, x of n equal to cos of 2 pi n divided by 12. Here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this 12 came here, this point 12. So cos of 2 pi n divided by 12. Then cos of x of n equal to cos of 8 by n divided by 3 1. So here according to this waveform, and see x of n equal to cos of n divided by 6. So here like this n divided by 6. So to gain some additional insight into these properties, let us examine again the signals depicted in figure 1.2. Now we have seen. First, consider the sequence x of n equal to cos of 2 pi n divided by 12 depicted in figure 1.25a. X of n equal to cos of 2 pi n divided by 12. This is okay, which we can think of as the set of samples of the continuous time sinusoidal x of t equal to cos of 2 pi t divided by 12 at integer time points. This is happening in we can think as the set of samples as the continuous time sinusoid x of t equal to cos of 2 by t divided 12. This is in discrete time happening. Here continuous time 12 at integer time points. In this case x of t is periodic with fundamental period 12. Periodic with fundamental period 12, and x of n is also periodic with fundamental period 12. Here periodic that is in this here fundamental period is 12. That is the values of x of n repeat every 12 points. Every 12 points repeating exactly in step with the fundamental frequency of x of t. 12 points repeat means from here to here 12 points complete. Then from here to here complete again. So periodic. This is the fundamental. Okay, and so on. So the values of x of n repeat every 12 points exactly in step with the fundamental period of x of t. In contrast, consider the signal x of n equal to cos 8 by n 31 divided by 31 depicted in figure 1.25b, which we can view as the set of samples x of t equal to cos of 8 by t divided by 31 at the integer points in the time. It is happening in samples of set of samples like this in a continuous time. In this case, x of t is periodic with the fundamental period 31 divided by 4. 31 divided by 4. On the other hand, x of n is periodic with the fundamental period 31. Fundamental period 31. The reason for this difference is that the discrete time signal is defined only for integer values of the independent variable. Thus, there is no sample at a time t equal to 31 divided by 4 when x of t completes one period starting from 0 to t equal to 0. Similarly, there is no sample at t equal to 2.31 divided by 4 or t equal to 3.31 31 divided by 4 when x of t has completed 2 or 3 periods, but there is sample at t equal to 4.31 divided by 4 equal to 31 when x of t has completed 4 periods. In contrast, consider the signal x of n equal to cos of 8 by 31. Cos of 8 by 31. 8 by 31 depicted in figure 1.25, which we can see view set of samples of x of t equal to x of t equal to x of t in another continuous signal x of t equal to cos of 8 by t divided by 31 at an integer points in time. In this case, x of t is periodic. X of t is periodic with fundamental period 31 divided by 4. 31 divided 4. On the other hand, x of n is periodic with the fundamental period 31. Fundamental period 31. Fundamental period 31. The reason for the difference is the discrete time signals defined only for integer values of the independent variable. Thus, there is no sample at the test 31 point divided by 4 when x of t completes one period. X of t completes one period starting from t equal to 0. Similarly, there is no sample at t equal to 2.31 divided by 4, t equal to 3.31 divided by 4 when x of t has completed 2 or 3 periods, but there is sample at 4.31 divided by 4 equal to 31. 31 when x of t has completed 4 periods. This can be seen in figure 1.25 where the patterns of x of n values does not repeat with each single cycle. that is where the patterns of x of n value say does not repeat with each single cycle of positive and negative values. Positive and that is here, for example, here coming, so here one here coming after this one, not immediately coming, not immediately plus or minus alternative coming. So that's why here telling the pattern where the pattern x of n values does not repeat with the each single cycle of positive and negative values. Each does not repeat with each single cycle of positive and negative values. That is, this is start from here. So yeah, the end positive signal, then negative. So that's why they are telling rather not repeat with each single cycle of positive and negative values. Rather, the pattern repeats after 4 such cycles, namely every 31 points. After 31 point only it will be repeat. The pattern repeats after uh, 4 such cycles, namely 31 points. Similarly, the signal x of n equal to cos of n divided by 6 can be viewed as the set of samples of the signal x of t equal to cos t by 6 at the integer time points. In this case, the value of x of t at the integer sample points never repeat as these sample points never span an interval uh, that is an exactly multiply of period 12 pi of x of t. Thus, x of n is not periodic. Here, x of n is not periodic. Although the eye visually interpolates between sample points suggesting the envelope x of t which is periodic. The use of the concept of sampling to gain insight into the periodicity of discrete time sinusoidal sequences explored further in problem 16. Problem 1.36. Okay. Example, suppose that we wish to determine fundamental period of the discrete time signal x of n equal to e power j of 2 pi divided by 3 into n plus e power j of 3 by divided by 4 into n. Here the first exponential on the right hand side of the equation in 1.59 has fundamental period of 3. While this can be verified from equation 1.58, there is a singular way to obtain that answer. In particular, note that a single note that angle 2 by 2 by divide 3 into n of the first term must be incremented by multiple of 2 pi for the values of